All right, here is 6-2, day 2. Topic's going to be adding and subtracting two variables. Just for space here, I'm going to put it down at the bottom. Give you a couple definitions, and then we'll work through a couple examples. So up at the top, you have the sum, okay? If you're dealing with the mean, okay? And it's pretty straightforward. What the notation it's using here, and I don't care if you use the expected value or not. We typically stick with mu. But you've got this new variable t, that's the total of adding up the other two. Okay? If you were to do that, you just add your means. Okay? Or, I'm going to add to this definition, you could have mu sub d, which would be the difference. Which would be mu of x, let's call that your first variable, minus mu sub y, if you're taking those two variables and subtracting them. Okay? So basically, if you're adding two variables, add your means. If you're subtracting two variables, subtract your means. It's pretty straightforward. I'll show you an example of each. Okay? Now, the standard deviation is a little bit of a different story. We could add to this definition that this is really for the sum or difference. Okay? What it's basically saying is you are permitted to do one thing. You can add variances, and that's it. Okay? And you do it no matter what, whether the two variables are added or subtracted. Now, a formula that's not on your packet, so this would apply to t or d, whether it's a total or a difference. You may want to think about it this way. If you have sigma sub x squared plus sigma sub y squared, throw it underneath a big square root and you have your new standard deviation. Okay? Pay attention to the note at the bottom. You can't add standard deviations, okay? Ever. All right, all you can do is just add variances. The fact that it's under a big square root is kind of an issue for addition. That's why we have to kind of switch over to variance, then we could add it together. I'll show you one of each here. So this one can be really, really tricky because you look at it and it kind of feels like multiply by a constant, like that we should multiply by 12. The issue here is that we randomly select 12 apples. So it's like 12 separate random selections. Okay, so we know for one of the apples the mean is 9, and we have to add, because we're selecting from the same distribution, we have to add this mean to itself 12 times because we're going to pick 12. So there, the quick way to do it would be 9 times 12, which would give you a mean of 108. Okay? It's easy to get caught up thinking with sigma that, okay, we take 1.5 times 12. Okay, but that's not what we're going to do. Underneath a big square root, what would happen is we'd have the variance, which is 1.5 squared, plus 1.5 squared, okay, and we continue. The shortest way to say it is you would have 12 times 1.5 squared. Okay, you would add up that variance 12 times. Because this is like taking the same random variable and adding to itself 12 times. So it has to be treated this way. And then you'll see for sigma, right, if you multiply by 12, you'll get 18. If you add it together, you'll get 5.2. You get a very different standard deviation. The means kind of come out to be the same, but standard deviation is a really different story. Okay, you should end up with 5.2. Once you have that, it's pretty straightforward stuff. Okay. Again, you may want to highlight that calculation for sigma. Okay. Really, what the way you could tell that this is addition is usually if the transformation involves multiplying by a constant, they give you some kind of formula that tells you, hey, this is what you did to your data. And that here, that's not the case. Like the 12 is coming from 12 separate random selections. They just happen to be from the same distribution. It did say that this distribution was normal. Centered at 108 with a standard deviation of 5.2. We are looking for this probability that we get 12 and they weigh under 100 ounces. At this point you'd be off to your normal CDF. Oops. You should get something right around 0.062, or about a 6% chance that our bag of 12 will weigh less than 100 ounces, right? And there's your interpretation for it. Okay, about a 0.062 chance that 12 randomly selected apples will have a total weight, right? Again, total of adding the 12 together kind of tells you that, hey, you need to think of it as adding up 12 separate selections, not multiplying by 12, to get a total weight of less than 100 ounces. All right, and to finish here, we'll do a difference. This one's a little bit easier to tell because the selection is from two separate distributions. And this is the more common case. That last one with the apples, to identify that it was based on adding the same variable to itself 12 times, that was a tricky one. Here, if you're selecting from two separate distributions, it's a lot more clear because it tells you two means and two standard deviations. So you're like, hey, I have two variables. I'm probably doing something with those two, right? And the only options we have are to add them or to subtract them. That's all we got. Okay? Now I'm going to say right here that I'm going to define the difference as male minus female. Okay? So that means for my mean, I'm subtracting these two variables to get a new distribution that will still be normal, and it will be centered at 5, which would tell you that if you were randomly to select a male and a female speed dater, we'd expect the male to be 5 inches taller, on average. Of course, that's going to vary. That's what we're going to calculate next, is how much that's going to vary. We could do 3.5 squared. Remember, it doesn't matter that I'm subtracting. I'm still essentially adding the variances. Okay, I do it underneath the square root so that when I'm done with this calculation, I have my new standard deviation, which will be 4.61 inches. And that's really like the only new extra work you have to do, because based on the fact that I was subtracting these two variables, I just needed the mean and the standard deviation of them. Because I know the shape is going to be normal, so I get my normal curve all set up, centered at 5. Sigma is 4.61. Now the question was, what are the odds that the male will be taller? What are the odds the male will be taller? This kind of goes back up here. You got 3 cases you could think about. If D was 0, what if D is positive, and what if D is negative? Okay? If you got a difference of 0, that means the 2 randomly selected speed daters were the same height. Okay? If D is positive, that means the male was taller. And if the difference was negative, that means that the female was taller. Okay? The question that it's posing to us is, what are the odds that the male is taller? The spot I want to mark is still D equals 0. Okay? That's where they're the same height. That's like my cutoff. Everything to the left would be negative, so those are female, cases where the female was taller. Everything to the right is positive, and that's where the male would be taller, and it's this area here that I'm shading. That's what I'd be looking for. Okay? But it's normal. I've got a mean, standard deviation, a lower bound of 0, and an upper bound of some crazy huge number, and we could get it. You'd head over to the normal CDF, and you'd get about 0.86. Okay? So that was a look at a problem where we were subtracting 2 variables. And again, that apple problem, we were technically adding variables together, but it was totally fine that we were adding the same variable to itself, which you could see happen.